In the last part of chapter 2, I'm going to talk to you about a concept called coding. Now, coding is something that was particularly useful in the days before computers. If you had a series of data values and you wanted to analyse them, but they were all very large, that would have been quite time consuming. What people would do would be to code the data. That's a way of transforming the data into smaller values and then performing analysis on those smaller values and then decoding the analysis in order to work out what the equivalent statistics would have been for the original set. So imagine your original set was X. You might subtract something from all of the values, you might divide them all by something, and that would give you a new set of data, let's call it Y. You would then work out, say, the mean or the standard deviation of this new smaller set of data, and you would use that smaller mean or standard deviation to work out the original mean or standard deviation of the larger data. Now, these days, these calculators make it very easy for us to work with any size of numbers. We don't really have to think about coding too much, but it's a very useful thing to be aware of, and it's a useful thing to be able to do. So, I'm going to go through it first of all with an example that's not in the book, because I want to talk a little bit about the effect of coding and how it affects the mean and the standard deviation. So I've got a data set here, a very simple one. We've called all these values X. They go from 101, increasing by 1 to 106. So the mean of these data would be 103.5. Standard deviation, I don't think I can do that one in my head, so let's do it on the calculator. Single variable statistics, let's go with that, and we'll enter them in. And then we'll work out our calculations from it. So we can see our mean is 103.5. Our standard deviation is 1.71 to 2 decimal places or 3 significant figures. Just realised I never mentioned what this symbol is. Let's do a little aside up here. This symbol here is a Greek letter sigma, a capital one. This one is also the Greek letter sigma, but it's the lowercase one. And this is the one we use for standard deviation, and of course we know that we use sigma squared for variance because of the relationship between standard deviation and variance. So this symbol for standard deviation is a lowercase Greek sigma. So coming back to these data now, we knew our mean and standard deviation for the original data. First of all, we're going to code all these data into a variable I've called y1. So we're going to code them by subtracting 100 for them all, which makes them all 1, 2, 3, 4, 5 and 6. Now, let's work out the mean and the standard deviation for these data. Our mean, y1 bar, is going to be 3.5. And look at the relationship between the original mean and this mean. This one is 100 less than this one. So that's suggesting to us that when we code a data by something like subtracting 100, it also subtracts 100 from the mean. Now let's work out our standard deviation of the variable y1. So sigma with a little subscript y1 there. Let's come to the calculator for it. We have got 1, 2, 3, 4, 5, 6. I can see there that our standard deviation is again 1.71. So it's the same as the standard deviation of the original data. So why is that? We've made all these numbers smaller, but our standard deviation hasn't changed. Well, let's think about what's going on here and what the standard deviation measures. It measures how spread out these numbers are from the mean. Look at the original data sets. The mean was 103.5. So when we're thinking about how spread out they are, these values go 0.5 above and below, 1.5 above and below, 2.5 above and below. Now look at this set, 3.5 here, and they go 0.5 above and below, 1.5 above and below, 2.5 above and below. So the spread of these data is identical to the spread of these data. So we would expect the standard deviation to be the same. So adding and subtracting doesn't affect your standard deviation, but it does affect your mean. Now let's look at a different way of coding the data. This time I'm going to take my x values again and I'm going to divide them by 100. So we've got 1.01, 1.02, and so on. So let's work out the mean and the standard deviation of my set y2. Its mean is going to be 1.035. Now let's compare that to the original mean, which is 103.5. You can see that this one is 100 times smaller than this one. So we've taken our original mean divided by 100, which fits the code. So again, the mean has been, of the coded data, is transformed by this code. The mean of the original data is transformed by this code to give us the mean of the coded data. How does it affect the standard deviation though? Now, stop and think about this before we put it in the calculator. Are these data as spread out from the mean as the original data, or the ones above, which have the same standard deviation? You can see they're not, because from 1.035, the lowest we go down here is 1.01. That's a much smaller gap than going from 3.5 to 1. A much smaller gap. So I can immediately see that my standard deviation is going to be smaller. I'm going to make a guess here, and I think the standard deviation is going to be 100 times smaller because our code was divided by 100. So let's double check. Entering the data. Single variable calc, and the standard deviation is 0.0171. Which is 100 times smaller than the original standard deviation. So yeah, the standard deviation is affected by this code, which was dividing. It wasn't affected by the one where we subtracted, it has been affected by the one where we divided. Now think about why. If you take a set of numbers like this, and you divide them all by something, the numbers you get are much closer together than the numbers you started with, which means the spread is automatically smaller. If you're struggling to see that idea, let's just do an example a different way over here. If we have the numbers, let's take 1, 2, 3, 4 and 5, and I times them all by 10, for instance, we get 10, 20, 30, 40, 50. Clearly these 5 numbers are more spread out than those 5 numbers were. So timesing and dividing affects how spread out your numbers are, whereas adding and subtracting doesn't. Adding and subtracting just shifts the same spread up or down the number line without spreading it out or compressing it at all. So far it seems to be that the mean is affected by adding and subtracting and timesing and dividing, whereas the standard deviation is only affected by timesing or dividing. So my third code combines the two ideas, and let's see if it's the case. Let's see if this holds. So we are going to go back to our x values, subtract 100 from them all, which would give us these, 1, 2, 3 to 6, and then we're going to divide them all by 2. So our y3 data set looks like this. So let's have a think about the spread. Is this as spread out as my original data set, or indeed this one, which had the same spread? Clearly it's not. Clearly, to get from our mean here, which is 1.75, down to 0.5, is a smaller jump than to get from 3.5 to 1 or 103.5 to 101. So yes, the standard deviation has been affected. Of course, the mean will be different because these numbers look completely different. So let's write down what our mean will be and our standard deviation. Let's put the data set in from scratch. We've got 0.5 going up in 0.5s up to 3, and we can see that the mean is 1.75 and the standard deviation is 0.854 to 3 decimal places, which is half of the standard deviation we had originally, and that agrees with this idea of dividing by 2. But look, it's literally only half of the original one. This minus 100 has not affected it at all. So this is really key now. The mean is affected by adding, subtracting, timesing and dividing. All 4 calculations affect the mean. However, the standard deviation is only affected by multiplying and dividing, because those are the ones that either compress or spread out the numbers. Adding and subtracting just shifts the whole thing along the number line and doesn't change how spread out it is. So adding and subtracting do not affect the standard deviation. Now let's go and look at the questions from the book. So in our first question, we have our data set here called X, and we're told that the data are coded using X minus 300 divided by 10. So firstly, we want to write down what the new coded data set Y is. So we're going to subtract 300 from each of these, which gives us in the first one 32, and then divide by 10, so the first one would be 3.2. The next one is going to be 55 over 10, 5.5. The next one would be 6 over 10. The next one 17 over 10, and the next one 40 over 10. So we've got our new set of data. These numbers are smaller, so arguably a little more easy to deal with. Now we've got to find the mean and the standard deviation of the coded data in part B. And then in part C, we're going to use that to find the mean and standard deviation of the original data. So this is our coded data. We're going to find its mean first by using the sum of y over the number of data points. So let's add these up. I'm going to put my calculator back into normal mode because I'm going to do this manually. We've got 15 for the sum of all the values, and we have 1, 2, 3, 4, 5 of them. So the mean of these coded data is 3. Now let's find the standard deviation. So remember, for the standard deviation, we're going to need another statistic here. We need to know the sum of y, which is 15. We also need to know the sum of y squared. So we're going to square all of these and add them up. If I just go back through my calculator here, where I'm adding them up, I could just add a square on the end of them all like that. And that gives me 59.74 for my sum of y squared. Now, see if you can remember the standard deviation formula. We need to do the sum of y squared over n minus the mean squared. But then that's for variance. For standard deviation, we square root it. So we've got 59.74 over 5 minus our mean, which was 3 squared, and then square root it. So that gives me, for the y, the coded data, a standard deviation of 1.72 to 3 significant figures. Were we given any context for these? I'm thinking about units at the moment, so if we go back and look. Yeah, it's the temperature at 5 different points in a nuclear reactor, and they're all given in degrees Celsius. So both of these should have units of degrees C on them. Now, what we're asked to do next is to use the coded mean and the coded standard deviation to find the mean and standard deviation of these original data here. So what we have to remember is which of these two parts of the calculation in the code affect the mean and which affect the standard deviation. Now we know that the mean is affected by everything: add, subtract, times and divide. So what I'm going to do is I'm going to write this code but using the means instead. But we know y bar, we know that that's 3. So we've got 3 equals x bar minus 300 over 10. And all we're doing now is we're going to undo the code. We're going to reverse it. So we're going to multiply the 10 up, and then we're going to add the 300. So that tells me that x bar is 30, add 300, 330. So I've got my original mean. Now I'm going to do the same for the standard deviation, but the standard deviation is only affected by multiplying and dividing. So the only thing I'm going to undo here is this divide by 10. So my coded standard deviation was 1.72, which tells me that my original standard deviation for x is going to be 1.72 times 10, because we're undoing a code of divide by 10. So my original standard deviation would be 17.2 degrees. And think about what each of these mean. What they mean is for these temperatures taken in the nuclear reactor, the mean is 330, but all the other temperatures vary from that mean on average by about 17.2 degrees. So finally, let's have a look at example 11, which is another one just checking that you understand the kinds of things that affect the mean. We are given a little bit of information from the large data set. We're talking about G here, which is the maximum gust in knots, and it's recorded in Lucas during May and June 2015. But whatever these data values are, they are coded by subtracting 5 from all and dividing them all by 10. And when they're coded, we are then told these bits of information. We're told that SHH is 43.58, that H bar, that's the mean, is 2, and the N is 61. So what do we know already? We know that there are 61 readings that have been taken. These readings are all called G, but they are coded by subtracting 5 and dividing by 10. And the coded data have a mean of 2. And this, if you remember, is part of our standard deviation calculation. This, we've seen it with x so far, but the letter is irrelevant, is the sum of h minus h bar squared. So it's the difference of all of the h values from the mean squared. And that's part of one of the versions we have of the standard deviation formula. In fact, I have here, where we looked at this originally, in terms of x, that's this calculation. And we said that the variance is this calculation divided by n. So we can get the variance from this straight away by dividing by how many data values we have in our set. So we're asked to find the mean and the standard deviation of G. So we're asked to find G bar and we're asked to find sigma G. So in order to find G bar, let's take H bar, which is 2, and remember what parts of the coding affect the mean. And that's all of it. So let's write out our coding formula, but with the means instead. Put in H bar as 2. Solve this equation, so times by 10 to get 20, and then add the 5. So that gives me that our mean of G is 25, and the units here were knots. So our mean gust, maximum gust, is 25 knots. Now we'll do the same to find the standard deviation of these gusts. We're told that SHH is 43.58, and we're told that N is 61. So we can find the variance of H by using SHH over N. Oh, I don't think this is going to come out as a nice number, so I might just keep it like that for a moment. 43.58 over 61. There we go. That's the variance though, don't forget. So it's approximately 0.714. So I want the standard deviation, which is the square root of the variance. So the standard deviation is 0.845, etc. But that's for the coded data. So for the original data, we look at our code and we go, which parts of this affect the standard deviation? It's only the timesing and dividing. We were dividing by 10 in our code, so we want to reverse that dividing by 10. So I can say that the standard deviation of the original data is this one, times by 10, so we get 8.45 knots. Now let's just remind ourselves what these numbers mean, because I keep doing this, it's really important. You need to understand what they mean in context. So we had maximum gust in knots from the large data set. We had 61 readings taken. The mean of all those 61 readings was 25 knots, but all the readings varied, or they were spread out on average by around 8.45 knots from this mean. Some were above, some were below. This is a measure of the kind of average spread from the mean. So now you can have a go at exercise 2F, and that finishes off chapter 2.